fundamental theorem of calculus comes in two parts. One part talks about the integral of a derivative, the other part talks about the derivative of the integral. Now, these are sometimes called the first and second fundamental theorem of calculus, or fundamental theorem of calculus version 1 and version 2. And for some reason, they always do version 1 before version 2, even though version 2 is the really useful theorem that you use all the time, and version 1 comes up once in a while. So we're going to do the useful one first, which is the second fundamental theorem of calculus. And it says that if you have a continuous function and you want to compute its definite integral from a to b, then the way to do that is to find an antiderivative and evaluate that antiderivative at the endpoints. In other words, the definite integral of little f from a to b is the change in big F. Or put another way, the integral of the derivative of big F is the change in big F. Okay, now this is far and away the most useful way to find definite integrals. So for example, let's suppose we've got the function little f of x equals 1 over 1 plus x squared. And we want to evaluate the integral from 0 to 1 of little f of x dx. Now, you could do it by slicing this into little pieces, picking a point in each little interval, evaluating little f of x at that point, multiplying it by the width of the interval, adding them all up, and then taking a limit as you slice up finer and finer and finer and finer. Not easy. It can be done, but it could take you years. Instead, we're going to use the fundamental theorem. Can you think of a function whose derivative is 1 over 1 plus x squared? Well, the derivative of arctangent is 1 over 1 plus x squared. So, this is big F of 1 minus big F of 0. So that's the arctangent of 1 minus the arctangent of 0. And that's pi over 4 minus 0. And that's pi over 4. So the area under the curve between 0 and 1 is pi over 4. Now, I did something sneaky. I said the antiderivative. There's actually a bunch of antiderivatives. What if somebody said, let's use that antiderivative instead? It's just as good as the first one. The derivative of this function is 1 over 1 plus x squared. Well, then the fundamental theorem of calculus would still work. You'd still get big F of 1 minus big F of 0. Only now, big F of 1 would be the arctangent of 1 plus 3. And the arctangent of 0, big F of 0 would be the arctangent of 0 plus 3. So we'd get pi over 4 plus 3 minus 0 plus 3. And it would still give you pi over 4. The point is that the change in this function is the same as the change in this function. The constant comes along for the ride. So you can use whichever antiderivative you like the best and plug it in, and the fundamental theorem of calculus will still work. So why does it work? Well, the idea is that the whole change is the sum of the little changes. So let's take the interval from little a to b and break it up into a whole bunch of pieces. So we call the first piece x sub 0. We call the last piece x sub capital N. And we want to figure out how much big F changes from here to here. Now, the change in something from now till next year is a change today, plus a change tomorrow, plus a change the next day, plus a change the next day, plus a change the next day, plus a change in the last day. The whole change, the change from the starting point to the end point, is the sum of the partial changes. This change in the first step, the second step, the third step, the fourth step, and so on. And now this we can evaluate, because the change from here to here is the rate of change in here times the width. In fact, the mean value theorem says that there is a point somewhere between x1 and x0, let's call it x1 star, such that the derivative of big F at that point is big F of x1 minus big F of x0 divided by the delta x. And likewise, this difference is big F prime of some other point, let's call it x2 star times delta x, and so on down the line, plus big F prime of xn star times delta x. But what's the derivative of big F? That's just little f. So this is little f of x1 star times delta x plus f of little x2 star times delta x, and so on, plus f of xn star times delta x. Now this is starting to look like an integral. We've got big F of b minus big F of a is the sum, as I goes from 1 to n, of f of xi star times delta x, where delta x is b minus a over n. And now if we take the limit of both sides, the limit of this, well, this doesn't depend on n, so the limit of this is f of b minus f of a. And that is the limit as n goes to infinity of this sum, I equals 1 to n f of xi star times delta x. And by definition, that is the integral from a to b of f of x dx. So that's the fundamental theorem of calculus. A definite integral can be evaluated by finding an antiderivative and plugging it in at the endpoints. If you know antiderivatives, you know how to do definite integrals.